Polynomial Introduction. In class 9, you have studied polynomial in 1 variable and 3 degree. Recall that if px is a polynomial in x, the highest power of x in px is called the degree of the polynomial px. For example, 4x plus 2 is a polynomial in the variable x of degree 1. 2x square minus 3y plus 4 is a polynomial in the variable y of degree 2. 5x cube minus 4x square plus x minus under 2 is a polynomial in the variable x of degree 3, and 7 u power 6 minus 3 by 2 upon u power 4 plus 4u square plus u minus 8 is a polynomial in the variable u of degree 6, expressed like 1 upon x minus 1 under root 2 plus 1 upon x square plus 2x plus 3 etc. are not polynomial. A polynomial of degree 1 is called a linear polynomial. For example, 2x square minus 3 under root 3x plus 5 by plus under root 2 x minus 2 upon 11 3z plus 4 2 upon 3 u plus 1 etc. all linear polynomial. Polynomial such as 2x plus 5 minus x square, x cube plus 1 etc. are not linear polynomial. A polynomial of degree 2 is called quadratic polynomial. The name quadratic has been derived from the word quadrate, which means square. 2 square plus 3x minus 2 upon 5, y square minus 2, 2 minus x square plus 3 under root 3x, u upon 3 minus 2u square plus 5 under root 5 into b square minus 2 upon 3b 4z square plus 1 by 7 are some example of quadratic polynomial whose coefficient are real number. More general, any quadratic polynomial in x is of the form ax square plus bx plus c, where a, b, c are real number and a does not equal to 0. A polynomial of degree 3 is called a cubic polynomial. For some example of a cubic polynomial are 2 minus x cube under root 2 x cube, 3 minus x square plus x cube, 3x cube minus 2x square plus x minus 1. In fact, the most general form of the cubic polynomial is ax cube plus bx square plus cx plus d, where a, b, c, d are real number and a does not equal to 0. Now consider the polynomial px is equal to x square minus 3x minus 4. Then putting x is equal to 2 in the polynomial, we get p putting 2 is equal to 2 square minus 3 into 2 minus 4 is equal to minus 6. The value minus 6 obtained by replacing x by 2 in 2x square minus 3x minus 4 is the value of 2x square minus 3x minus 4 at x is equal to 2. Similarly, p0 is the value of px at x is equal to 0, which is minus 4. If px is a polynomial x and if k is a real number, then the value obtained by replacing x by k in px is called the value of px at x is equal to k and is denoted by p bracket k. What is the value of px square is equal to x square minus 3x minus 4 at x is equal to minus 1? We have, if we put minus 1 in p, so p minus 1 is equal to minus 1 square and minus bracket 3 into minus 1 bracket close minus 4 is equal to 0. Also note that p putting 4 is equal to 4 square minus 3 into 4 minus 4 is equal to 0, as p under root minus 1 is equal to 0 and p under root 4 is equal to 0. Sorry, here it is not under root, it is bracket. P bracket minus 1 is equal to 0 and p bracket 4 is equal to 0. Minus 1 and 4 are called the zeros of quadratic polynomial x square minus 3x minus 4. More generally, a real number k is said to be a zero of a polynomial px if pk is equal to 0. You have already studied in 9 how to find zeros of linear polynomial. For example, if k is a zero of px is equal to 2x plus 3, then pk is equal to 0 gives 2k plus 3, k is equal to minus 3 by 2. In general, k is a zero of px uh, is equal to ax plus b, then pk is equal to ak plus b is equal to 0. K, so the zero of polynomial ax plus b is equal to minus b upon a minus constant term upon coefficient of x. Thus, the zero of polynomial is related to its coefficient. Does this happen in this case of other polynomial too? For example, are the zero of quadratic polynomial also related to its coefficients? In this chapter, we will try to answer this question. We will also study the division algorithm for polynomials. 2.2 Geometrical meaning of the zeros of polynomial. You know that a real number k is a zero polynomial px if p is equal to 0, but why are the zero polynomial so important? To answer this, first we will see the geometrical representation of linear and quadratic polynomial and the geometrical meaning of their zeros. Consider first a linear equation ax plus b where a does not equal to 0. You have studied in class 9 the graph of y is equal to ax plus b is a straight line. For example, the graph y is equal to 2x plus 3 is a straight line passing through the point minus 1 minus 2 minus 2 minus 1 and 2 7. So if we put x is equal to minus 1, then by minus 1, if we put x is equal to 2, then by is equal to 7, and it is from the equation 2x plus 3. You can see that graph of y is equal to 2x plus 3 intersect x-axis and midway between x is equal to minus 1 and x is equal to minus 2, that is at the point minus 3 upon 2 and 0 bracket close. You also know that the 0 of 2x plus 3 is minus 3a by 2, thus the 0 of the polynomial 2x plus 3 is the x coordinate of the point where the graph of y is equal to 2x plus 3 intersects the x-axis. In general, for a linear polynomial ax plus b where a does not equal to 0, the graph of y is equal to x plus b is a straight line which intersects the x-axis at exactly one point, namely minus b upon a 0. Therefore, the linear polynomial x plus b a does not equal to 0 has exactly one 0, namely the x coordinate of the point where the graph of y is equal to ax plus b intersects the x-axis. Now let us look for the geometrical meaning of a zero of a quadratic polynomial. Consider the quadratic polynomial x square minus 3x minus 4. Let us see what the graph of y is equal to x square minus 3x minus 4 look like. Let us list a few value of y is equal to x square minus 3x minus 4 corresponding to a few value of x as given in table 10.1. Plotting of a graph of quadratic or cubic polynomial is not meant to be done by the student, nor it is to be evaluated. So here, if we put x value minus 1, minus 2, 0, 1, 2, 3, 4, 5, then by the equation x square minus 3x minus 4, so the value of y is come 6, 0, minus 4, minus 6, minus 6, minus 4, 0, 6 respectively. If we locate the point listed above on a graph and draw the graph, it will actually look like the one given in 2.2 figure. In fact, for any quadratic polynomial ax square plus bx plus c where a does not equal to 0, the graph of corresponding equation y is equal to x square plus bx plus c has one of two shapes, either open upward like or open downward like, depending on whether it does not whether a is bigger to 0 or a is smaller to 0. These curves are called parabolas. You can also see from table 2.1 that minus 1 and 4 are 0 of the quadratic polynomial. Also note from figure 2.2 that minus 1 and 4 are the x coordinate of the point where the graph of y is equal to x square minus 3x minus 4 intersect the x-axis. Thus, the zeros of the quadratic polynomial x square minus 3x minus 4 are x coordinate of the point where the graph of y is equal to x square minus 3x minus 4 intersects the x-axis. This fact is true for any quadratic polynomial. The zero of quadratic polynomial ax square plus bx plus c, where a does not equal to 0, are precisely the x coordinate of the point where the parabolas representing y is equal to ax square plus bx plus c intersect the x-axis. From our observation earlier about the shape of the graph of y is equal to x square plus bx plus c, the following three cases can happen. Case 1. Here the graph cuts axis at two distinct points A and A dash. The coordinate of A and A dash are the two zeros of the quadratic polynomials ax square plus bx plus c in this case. Here the graph cuts the x-axis at exact one point and two constant points. So the 2 point A and A dash of case 1 coincide here to become 1 point A. The x coordinate of A is only 0 of the quadratic polynomial ax square plus bx plus c in this case. Case 3. Here the graph is either completely above the x-axis or completely below the x-axis, so it does not cut the x-axis at any point. So the quadratic polynomial ax square plus bx plus c has no 0 in this case. So you can see geometrically that a quadratic polynomial can have either two distinct zeros or two equal zeros or no zeros. This also means that a polynomial of degree 2 has almost two zeros. Now, what do you expect the geometrical meaning of the zeros of a cubic polynomial to be? Let us find out. Consider the cubic polynomial x q minus 4x. To see what the graph of y is equal to x q minus 4x looks like, let us list a few value of a y corresponding to a few value of 4x in table 2.2. Here x and x be put value minus 2 minus 1 0 1 2, and equation is y is equal to x q minus 4x and its result 0 3 2 minus 3 0 respectively. Locating the point of the table on a graph paper and draw the graph BC. The graph of y is equal to x q minus 4x actually look like the given in figure 2.6. We see from the table above that minus 2, 0 and 2 are 0 of the cubic polynomial xq minus 4x. Observe that minus 2, 0 and 2 are in fact the x coordinate of the only point where the graph of y is equal to xq minus 4x intersect the x-axis. Since the curve meets the x-axis in only one three point, their x coordinate are the only 0 of the polynomial. Let us take a few more examples. Consider the cubic polynomial xq and xq minus x square. We draw the graph of y is equal to xq and y is equal to xq minus x square in figure 2.7 and 2.8 respectively. Note that 0 is the only 0 of the polynomial xq. Also from 2.7 you can see that 0 is the x coordinate of the point where graph of y is equal to xq intersect the x-axis. Similarly, xq minus x square is equal to x square bracket x minus 1. 0 and 1 are the only zeros of the polynomial xq minus x square. Also from figure 2.8, these values are the x coordinate of the only point where the graph of y is equal to sq minus x square intersects the x-axis. From the example above, we see that there are at most three zeros of any cubic polynomial. In other words, any polynomial of degree 3 can have at most three zeros. Remark: in general, given a polynomial px of x of degree 9 n, the graph of y is equal to px intersect the x-axis at almost n point. Therefore, a polynomial px of degree n has at most n zeros. Example: now, relationship between zeros and coefficient of a polynomial. You have already seen the zero of a linear polynomial ax plus b is minus b upon a. We will now to answer the question raised in section 2.1 regarding the relationship between zeros and coefficient of a quadratic polynomial. For this, let us take a quadratic polynomial. Say px is equal to 2x square minus 8x plus 6 in class 9. You have learned how to factorize quadratic polynomial while splitting the middle term. So here we can need to split the middle term minus 8x as the sum of two terms whose product is 6 into 2x square is equal to 12x square. So we write 2x square minus 8x plus 6 is equal to 2x square minus 6x minus 2x plus 6 is equal to 2x under root x minus 3 minus 2 under root sorry it's 2x square minus 8x plus 6 is equal to 2x square minus 6x minus 2x plus 6 is equal to 2x bracket x minus 3 bracket close minus 2 into bracket x minus 3 bracket close is equal to 2x minus 2 bracket close bracket x minus 3 bracket close is equal to 2 bracket x minus 1 bracket close bracket x minus 3 bracket close. So the value of px is equal to 2x square minus 8x plus 6 is 0 when x minus 1 is equal to 0 or x minus 3 is equal to 0 when x is equal to 1 or x is equal to 3. So the 0 of 2x square minus 8x plus 6 are 1 and 3. Observe that sum of its zeros is equal to 1 plus 3 is equal to 4 is equal to minus 8 bracket minus 8 bracket close upon 2 and it is equal to minus bracket coefficient of x upon coefficient of x square. The product of its zeros is equal to 1 into 3 is equal to 3 is equal to 6y upon 2 is equal to constant term upon coefficient of x square. Let us take one more quadratic polynomial. Say px is equal to 3x square plus 5x minus 2 by the method of splitting the middle term. 3x square plus 5x minus 2 is equal to 3x square plus 6x minus x minus 2 is equal to 3x bracket x plus 2 bracket close minus 1 bracket x plus 2 bracket close is equal to 3x minus 1 bracket close bracket x plus 2 bracket close. Hence the value of 3x square plus 5x minus 2 is 0 when either 3x minus 1 is 0 or x plus 2 is 0 is equal to when x is equal to 1 minus 3 or x is equal to minus 2. So the 0 of 3x square plus 5x minus 2 are 1 by 3 and minus 2. Observe that sum of its zeros is equal to 1 by 3 plus minus 2 is equal to minus 5 upon 3 and that is minus bracket coefficient of x upon coefficient of x square. and also product of its zeros. It means 1 by 3 into minus 2 is equal to minus 3 by 2. It is equal to constant term upon coefficient of x square. In general, if alpha and beta are the zeros of quadratic polynomial, px is equal to ax square plus bx plus c, where a does not equal to 0, then you know that x minus 1, x minus alpha and x minus beta are the factor of px. Therefore, ax square plus bx plus c is equal to 0 is equal to k bracket x minus alpha bracket close bracket x minus beta bracket close, where k is a constant. Now k bracket x square minus small bracket alpha plus beta small bracket close plus alpha beta bracket close, it is equal to kx square minus k bracket alpha beta bracket close x plus k into alpha beta. Comparing the coefficient of x square, x and constant term on both sides, we get a is equal to k, b is equal to minus k bracket alpha plus beta bracket close, and c is equal to k into alpha into beta. This gives alpha plus beta is equal to minus b upon a, and alpha into beta is equal to c upon a. And alpha beta are Greek letter pronounced as alpha and beta respectively. We will see later one more letter Yama. Zeros of polynomial. Sum of zeros is equal to alpha plus beta is equal to minus b upon a is equal to minus coefficient of x upon coefficient of x square. Also product of zeros is equal to at the rate alpha into beta is equal to c upon a is equal to constant term upon coefficient of x square. Let us consider some example. Please guys, you must read example. I am go to 2.4 division algorithm for polynomials. You know that a cubic polynomial has at most 3 zeros. However, if you are given only 1 zeros, you can find the other 2. For this, let us consider the cubic polynomial x cube minus 3x square minus x plus 3. If before you tell that one of its coefficient zeros is 1, then you know that x minus 1 is the factor of x square minus 3x square minus x plus 3. So you can divide x cube minus 3x square minus x plus 3 by x minus 1 as you have learned in class 9 to get the quotient x square minus 2x minus 3. Next you could get the factor of 2x square minus 2x minus 3 by splitting the middle term as x plus 1 x minus 3. This would give us x cube minus 3x square minus x plus 3 is equal to bracket x minus 1 bracket close bracket x square minus 2x minus 3 bracket close is equal to x minus 1 bracket close into bracket x plus 1 bracket close into bracket x minus 3 bracket close. So all the 3 zeros of cubic polynomials are now known to you as 1 minus 1 3. Let us discuss the matter of dividing one polynomial by other in some details. Before, notice the following is formally considered an example. Divide 2x square plus 3x plus 1 by x plus 2. Note that we stop the division process while either the remainder is 0 or its degree is less than degree of the divisor. So here the quotient is 2x minus 1 and remainder is 3. Also 2x minus 1 bracket close into x plus 2 bracket close plus 3 is equal to 2x square plus 3x minus 2 plus 3 is equal to 2x square plus 3x plus 1. Example example, 2x square plus 3x plus 1 is equal to x plus 2 bracket close bracket 2x minus 1 bracket close plus 3. Therefore, dividend is equal to divisor into quotient plus remainder. Let us extend this process to divide a polynomial by quadratic polynomial.